Hi everyone, today we'll discuss a question from the topic Law of Conservation of Momentum. Now, as we do this question, we will understand why when we propel rockets, all the gases are not thrown at once. We throw the gases continuously, isn't it? We don't throw all the gas at the same time. So let us try to understand why that is done through this question. So let's see what the question says. Here is a boat floating in water along with a boy and two stones. The total mass of this system, the boat, the boy and the two stones, is given capital M. Small m is mass of each stone. We are supposed to neglect friction on the boat from water. So there is no horizontal force acting on the system. Now, what the boy wants to do is he wants to gain speed in this direction by throwing the stones in the opposite direction. Basically, he's trying to make use of Newton's third law, right? If he throws the ball in this direction, the reaction of that force will act on the remaining part of the system in this direction, right? So if he throws the ball this side, he will feel reaction this side. And that is the basis of firing bullet from a gun, isn't it? When you fire the bullet forward, the gun will recoil backward, right? Now it is given the boy can throw the stone with speed u, but this u is not relative to ground, not with respect to ground, it is with respect to boy. So the question is, in order to gain more speed, should he throw both the stones at the same time, or should he throw the stones one by one? That is the question. Now let us discuss the first case where he throws both the stones at same time. The two stones together have mass 2m and the remaining part of the system will have mass total minus 2m, right? Now when he throws the stones in this direction, at that moment he will have a velocity v in this direction, right? Because of the reaction. Now we want to calculate this v, remember. Now I have taken this direction to be positive. So this velocity we know. What about velocity of the stones? Now remember students, whenever we apply conservation of momentum, we need to apply it from ground frame with respect to ground. And what is the velocity of the stone with respect to ground? Is it u? No. U was velocity of stone with respect to boy. So now we need to first calculate velocity of stone with respect to ground. What is the formula? Well, velocity of stone with respect to ground is given by the formula velocity of stone with respect to boy plus velocity of boy, isn't it? If you bring this VB this side, you will get the famous formula of relative velocity, VSB equal to VS minus VB. Now, what is the velocity of the stone with respect to boy? Well, it was given U, but in this direction. So I should write minus U, right? And velocity of the boy is in this direction, so it will be plus v. So remember, at the instant he throws the ball, at that instant itself it will have velocity v in the positive direction. Now since I want the stones to have velocity in this direction, I will write this as minus common u minus v. So minus means the stones are having velocity in this direction with respect to ground, and this is the speed of the stones with respect to ground. So that speed, let me show you, u minus v. So remember, this is the speed, the numerical value, and this minus sign means it is in this direction, right? Now let us apply conservation of momentum. Before, the system was at rest. So initial momentum of the system was 0. What will be the momentum now? Well, this one has momentum in positive direction, and formula of momentum is mass into velocity. But that velocity should be with respect to ground, remember. So m minus 2m is mass of the boat and the boy into velocity of the boy. Now this is in the opposite direction. So minus mass is 2m and the speed is u minus v. Right? So speed is u minus v, minus because it is in this direction, right? Now, if you consider the whole thing as a system, then there is no external force on this system along x-axis. Whatever friction may come from water, that we have to neglect. And whatever force the boy applies on the stones, that is internal force, not external. So therefore, since there is no external force along x-axis, momentum of the system should be conserved. That means final momentum should equal initial momentum of the system. Now what's the final momentum? Let's open this bracket, m into v minus 2m into v, and this side minus 2mu minus minus plus 2m capital V, and that is equal to 0. You can see minus 2mv and plus 2mv will cancel. If you take minus 2mu this side, you will get mv is equals to 2mu, and therefore the speed of the boy after he throws the stones will be 2mu by capital M. Let us now discuss case number 2, where he throws the stones one after another, not both at the same time. Now, the mass of one stone is m, so the remaining part of the system will have mass total minus m, remember, right? One stone is still here. And when he throws the stone that side, at that moment itself, it will acquire velocity this side, which I have written v dash. Now, velocity of the stone with respect to ground, like we saw before, was minus u minus v. Now it will be minus u minus v dash. The minus sign is simply saying that the direction is this side and this is the magnitude, which I have written here. Now, let us write conservation of momentum. Final momentum should be equal to initial momentum. Final for this part will be mass is m minus m. Velocity is positive this side, and for this momentum will be minus m u minus v dash, right? And this is in this direction. That's why I have put minus sign, and that should be equal to initial momentum was 0. Now simplify this, you will get mv dash minus mv dash minus mu minus minus will be plus mv dash equal to 0. And here minus mv dash plus mv dash will cancel. So v dash will be minus mu will go there, mu, and divided by this capital M. So this is the velocity after you have thrown the first stone. Now let's see what will be the velocity after you throw the second stone also. Now when he throws the second stone, can we assume he was at rest? No, because when he throws the second stone, he is already moving with velocity v dash, right? So just before throwing the second stone, initially he is already moving with velocity v dash, and the mass of the system is m minus m, right? Now he throws the second stone also with velocity u with respect to him, and at that moment he will acquire some new velocity, which I am writing v. So with respect to ground, the velocity of the stone will be u minus v in this direction, right? Now let us calculate the initial momentum of the system. So initial momentum is m minus m v dash, right? And the final momentum of the system will be m minus 2m, that's the mass of this remaining part, into v this side, and this will have negative momentum minus mass is small m, velocity with respect to ground is u minus v, right? Now we know from conservation of momentum, the final momentum of the system equals initial momentum of the system, and we know this is the final momentum and this is the initial momentum. V dash, remember, is the velocity of the boy after he throws the first stone, which we found mu by capital M before, right? So remember that. Let's simplify. Remember, I want capital V, so let me keep this one as it is, and minus mu, and this minus minus will be plus m capital V, and this one will be as it is. Now here and here I can take capital V common, right? So minus m minus 2m, and here plus m capital V common, minus mu take that side. So mu plus m minus m capital V dash. So this will give me minus 2m plus m will be minus m. So let me write here itself, right? So to find capital V, what I do now, divide by m minus m. So V will be here mu by m minus m plus m minus m v dash by m minus m. So these two will cancel. And v dash, let us substitute. What was v dash? Mu by capital M, right? So it will be mu by m minus m plus, what is v dash? Mu by capital M. Now let us compare the two cases. In the first case, when he throws both the stones at the same time, the final velocity was this, right? 2 mu by capital M. This was your case 1. And case 2, where he throws the stones one after another, the final velocity was this, right? Which, let me write this term first, mu by capital M plus mu by M minus M. Now, can you guess whether this is more or this is more? Well, that's quite easy to compare. You can write this one as mu by capital M plus mu by capital M, isn't it? This plus this will be this only. Now, see, the first term is same in both the cases. But here, the denominator is less than here. The numerator is same, but denominator here is less. If denominator is less, the ratio will be more. So V in case 2 is greater than V in case 1. And thus it is better to throw the stones one after another if you want to gain more velocity. What if there were 3 stones and we throw the stones one after another? Then the final velocity would have these two terms plus one more term would come, mu by m minus 2m. If you want, you can check it like the way we did, okay? And then this shows that if you have a series of stones, it is better to throw one by one than to throw all at the same time, right? Because here you can see the denominator is even less, so the velocity will be even more. And now I think you got the idea why we throw gases continuously and not all at the same time.